Hello all, welcome to this course on time series modeling and forecasting using R. Now again in this week we're sort of discussing the idea about multivariate time series processes, and then up to the last session we discussed some examples of, let's say, multivariate time series processes. So let's say VMA with a certain order, let's say VMA1 or VAR with a certain order, right? And we also discussed the combination. So let's say VARMA process of some orders PQ, etc. Right? So particularly this session is not on the easier side, right? Because up to now we have spent a lot of time on analyzing, modeling and forecasting univariate time series structures. But the whole idea is if you transition from a univariate situation to, let's say, even a bivariate situation or multivariate situation for that matter, then things become soon very difficult. So let's say you have to bring in the ideas of, let's say, random vectors or matrix theory and so on and so forth, right? Because each component in the underlying multivariate structure would be either a random vector or a random matrix, okay? Alright, so again just to give you a very quick review as to where we stand now. So up to the last session or towards the end of the last session, we were talking about VARMA process in general, which is nothing but a combination of an AR structure and the MA structure. And then we sort of put forward a case as to when can one say that a VARMA process is stationary, right? And there, if you remember, we brought in the idea of inverse of a matrix by writing down the inverse as 1 by determinant into the adjoint and so on and so forth, right? So the whole idea was by rewriting such Varma equation, right, we can actually make sure about the stationarity of the underlying process in easier ways, okay? Alright, so here the first thing we'll do in today's session would be we'll take up a concrete example from a bivariate situation. So we'll discuss a few things about this bivariate MA1 process, okay? And then again, of course, this is nothing but a VMA or rather V not A but then VMA1 process, right? So vector moving average process of order 1, right? But the only thing is that that vector only contains 2 elements, so hence it's called as a bivariate, okay? And then again, why bivariate? Because here if you see on the left hand side I have 2 random vectors. So the first one is y1t and then the second one is y2t, alright? So I can give you a very quick practical example. So let's say think of a situation where you want to sort of analyze 2 different time series processes. So let's say stock price of Reliance versus stock price of, let's say, Adani, right? And there you want to sort of analyze that how these 2 stocks co-behave or how are they sort of interdependent and so on and so forth, okay? And for doing all these things, we're putting forward a model called as a bivariate MA1 process, okay? So this is the numerical structure of that. So the first thing we require is a random error vector. So E1t, E2t minus the coefficient matrix. So 0.2 minus 0.4 minus 0.2 and then 0.6 multiplied by E1t minus 1 and then E2t minus 1, right? I mean, of course, this is the structure of any VMA1 process. So in general, VMA1 process is nothing but Yt equals, let's say, Et plus the theta 1 coefficient, if you remember, applied on Et minus 1, isn't it? So this is the VMA1 process which we even discussed in the last session, and then we are simply writing down this structure in a numerical way. So this is the actual numerical value of that. So Yt equal to the E1t and E2t random vector minus, now again this is nothing but my theta 1 matrix, right? So even as discussed in the prior session, all these coefficients, so theta 1, theta 2 or be it phi 1, phi 2 on the AR side, so all these are matrices now, okay? So theta 1 coefficient or rather theta 1 matrix multiplied by the Et minus 1 vector, okay? And here further we are assuming that sigma is 4114. Now what exactly is sigma? So sigma is nothing but the variance of my random error vector, okay? Because again remember this Et is what? So Et is not a univariate error, right? So Et is a multivariate or rather multivariate white noise process where the variance covariance matrix is given by sigma, okay? So this is that sigma. So we are defining sigma to be 4114, alright so far. So further from this expression I can gain insights into some covariance structures and so on and so forth. So again if you remember towards the very end of the last session we wrote down an expression for the autocovariant structure of a VMA1 process. Okay. So, what would happen if you take L to be 0? So, we described some cases there, right. So, L to be 0 or L to be 1 or L is bigger than equal to 2 and so on and so forth. Okay. So, firstly what would happen if your L is 0 or rather gamma of 0? So, gamma of 0 can be calculated easily by this expression. So, whatever theta 1 you have here, right. So, this is nothing but theta 1 into sigma into theta 1 transpose. So, expression is theta 1 into sigma into theta 1 transpose. And once you evaluate this, you will get 0.64 minus 0.92 minus 0.92 and then 1.28. Okay. So, this is nothing but gamma 0, and similarly if you extend it to what is gamma 1. So, gamma 1 is nothing but given by this expression, which is sigma into theta 1 prime. So, this is my sigma 4114 and this is my theta 1 prime. So, 0.2 minus 0.4 minus 0.2 and then 0.6, alright. And then this is nothing but 0.4 minus 0.2 minus 1.4 and 2.2. Right. And for all the further orders, so whenever L is bigger than equal to 2, my gamma L happens to be simply 0. Okay. So, this is just an empirical way of how do you visualize a bivariate process and then sort of write down a few initial values of the covariances there. Okay. Now, similarly further, let my matrix V take this form. So, my V is 0.6400 and then 1.28. And then here why do we require V? We require V such that we can actually find out autocorrelation matrices. So, my row 0 has this structure. So, V minus half, and by the way here what is this matrix? This matrix is nothing but that we saw on the first slide, which is right here. Okay. So, this matrix is nothing but gamma 0 in other terms, right. So, essentially my row 0 is nothing but V to the power minus 1 half multiplied by gamma 0 multiplied by V to the power minus 1 half. Okay. So, essentially my row 0 takes that form and then row 1 takes this form, right, and so on and so forth. Okay. So, hopefully the idea of from a moving average perspective should be clear now. So, we started with V ARMA process, then we sort of took some special cases, we discussed about the vector moving average process of a general order Q, and then we discussed VMA1, and then the last slide or in the initial few minutes of today's session we took up a practical example or a numerical example and explained VMA or rather bivariate MA process with order 1. Okay. Now, of course, the other side of the coin is explaining about vector autoregressive processes of a certain order P. Okay. And then this model structure is given by VARP. So, a vector autoregressive process of order P, or in short VARP, is given by this structure. So, yt equals some delta plus phi 1 into yt minus 1 plus phi 2 into yt minus 2, so on and so forth up to phi p into yt minus p plus the white noise error vector. Okay. And again as before, so all the phi I coefficients I going from 1 to p are nothing but k dimensional square matrices. So, all these coefficients are nothing but k dimensional square matrices. My Et is nothing but a k dimensional vector of residuals, or in other words vector of purely random processes at time t, and delta is nothing but vector of constants. Okay. So, here just to remember one important thing is that we are not anymore in a univariate kind of a structure. So, if you are transitioning to a multivariate structure, so the constant term would be a vector, all the coefficients would be matrices, my error or Et would again be a vector, and so on and so forth. Okay. So, hence my phi i's are nothing but a k dimensional square matrices, my Et vector is a k dimensional vector of errors or residuals, and my delta is nothing but a vector of constants. Okay. Okay. And then I can sort of write down the same VAR process of order P in a concise form. So, the concise form takes this expression. So, phi b applied on yt should be equal to delta plus Et. Okay. And what exactly is phi b coefficient? So, phi b coefficient is nothing but ik. So, ik is what, by the way? So, ik is nothing but an identity matrix of order k. So, you have ones on the diagonal and all the off diagonal entries are zeros. Okay. So my phi b coefficient becomes ik minus phi 1b minus phi 2b square minus phi 3b cube and so on and so forth up to phi p into b to the power p, right. And all these are sort of corollaries. So expectation of Et is 0, expectation of Et into Et transpose is sigma, and then expectation of Et into Et plus L transpose is 0. So what do you mean by that? So we are assuming that the means of my random error vector is 0, right, and the variance covariance matrix of the errors is given by sigma, and any of the cross covariances, so all the cross covariances are 0 because they are assumed to be independent. Okay. So something like Et into Et plus L transpose would be 0, and this should be true for all T and L which are not equal to 0, or rather for all T but then all L excluding the value of 0 basically. Okay. Okay. So now we will again try to sort of rewrite the initial equation. So now the very initial equation that we saw in the VAR structure could be slightly modified and then rewritten as probably something like this. So on the LHS what we have, so yt minus mu equals phi 1 yt minus 1 minus mu plus phi 2 yt minus 2 minus mu, and then dot 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 so on and so forth up to phi p yt minus p minus mu plus my error vector Et. Okay. But here just couple of things to note is that my delta, so you do not see any delta here, right. So you do not see a delta because I am expressing my delta to be nothing but phi I applied on mu, or rather my mu becomes phi I inverse applied on delta, right, which is nothing but given by this expression. So psi I applied on delta. Okay. Now the whole idea of sort of rewriting the initial equation is that under this condition one can actually have a MA representation. Okay. Okay. So one can actually have an MA representation which is given by that form. So yt becomes phi inverse b into delta plus phi inverse b into Et, and if you sort of re-express these, the inverses, they take this form. So yt is nothing but mu plus Et plus psi 1 Et minus 1 plus psi 2 Et minus 2 and so on and so forth up to infinity. Okay. So this can be written down again in a concise form in this manner. So mu plus psi b into Et. Okay. Now again, how are all these things happening? You have to sort of go back a slide or couple of slides and then borrow some equation from there and then see that how are we writing that equation in something like that form. Okay. Because again if you go back a slide, this is the initial equation we have, right. So yt equals delta plus all of that, right. Now the first thing I am doing here is that subtracting mu throughout. So what would happen if you subtract mu throughout? If you subtract mu throughout, then on the LHS I have yt minus mu equal to phi 1 yt minus mu plus phi 2 yt minus 2 minus mu, etc. right. And here I can write down some concise form. So my delta becomes phi I into mu, or rather my mu becomes phi inverse into delta, and this phi inverse I am denoting as a psi, which is psi I into delta. Okay. And under all these conditions I can express my yt as a MA infinity structure, alright. And then similarly I can put forward and then give some expressions for the autocovariances matrices and so on and so forth. But just one last point to mention, if you go back a slide, then so in other words, in the last session we saw that I can actually express a VMA1 process as a what? As a VAR process of order infinity, isn't it? So this we saw in the last class. Okay. Similarly, I can actually express a VAR process of order P as a VMA process of order infinity. Okay. So you can actually strangely see that a particular vector moving average process of order 1 can be re-expressed as a vector autoregressive process of order infinity, and similarly a vector autoregressive process of order P can be expressed as a vector moving average process of order infinity. So you have these two sort of back and forth relationships between the AR part of the model and the MA part of the model. Okay. Alright, so now once you sort of write down this expression, I can now talk about its autocovariance functions and so on and so forth. So my gamma YL, or which is nothing but the autocovariance matrix, takes this form, of course. So expectation of yt minus mu into yt plus L minus mu and transpose. Now assuming delta is 0, which implies mu is 0, right. So these two mu's become 0 here in the above expression. So in other words, my gamma YL reduces to expectation of yt into yt plus L transpose, alright, which can be written down or broken down further as phi 1 expectation of yt plus L minus 1 transpose plus phi 2 and then expectation of yt and then yt plus L minus 2 transpose up to that point. So phi p and then expectation of yt into yt plus L minus p transpose, and then the last expression here is expectation of et into yt plus L transpose. Now the whole thing I am doing here is that I am taking yt from here and then yt plus L from here, right, and then each yt and yt plus L has their own expressions from the last slide if you see, right, from here essentially, okay, because we are dealing with a vector autoregressive process, isn't it. So I can sort of write down a VAR structure for yt and a VAR structure for yt plus L and then sort of multiply in every term, okay. But for this reason it can be simplified further as something like this. So phi 1, so the first expression you see here is nothing but phi 1 into gamma y L minus 1, because lag is nothing but L minus 1, isn't it. So the gap between these two subscripts is nothing but L minus 1. So in other words, this expression is nothing but phi 1 into the autocovariance function at lag L minus 1. Similarly, if you go a step forward, how much is the lag here? So here the lag is L minus 2. So this the middle expression reduces to phi t or rather phi 2 into gamma y at a lag L minus 2. Similarly, the last thing can be written down as phi p into gamma y L minus p, and the last expression is sigma e. So sigma e denotes the variance covariance matrix for my error vector, which is et, okay. And hence I can talk about, let's say, gamma y 0. So gamma y 0 would be the above expression but taking the value of L to be 0. So gamma 0 is nothing but if you consider L to be 0. So if you blindly plug in L to be 0 in the above expression, what will you have? So you will have phi 1 into gamma y of minus 1 plus phi 2 into gamma y minus 2 and so on and so forth up to phi p and then gamma y minus p plus sigma e. Or as discussed in some previous session in this week, that gamma y minus 1 is exactly equal to gamma y 1 transpose, okay. So gamma y minus 1 is nothing but gamma y 1 transpose. Similarly, gamma y minus 2 is gamma y 2 transpose, and similarly gamma y minus p is gamma y p transpose, and then plus you have this sigma e, okay. Thus I can again sort of summarize all the values. So gamma y 0 takes this form, which is again given in the last slide. Gamma y 1, so gamma y 1 means what? So L equal to 1, isn't it. So if you plug in the value of L to be 1, the expression that you get is this. So phi 1 gamma y 0 plus phi 2 gamma y minus 1, so on and so forth up to phi p gamma y minus of p minus 1. And in short, the last thing would be gamma y p in general, which is given by that expression, okay. So hopefully this is clear, and then I think here I am missing, or probably not, because you are sort of evaluating this at lag 1, so there won't be any sigma e component there, okay. But in general, my small gamma ijl, so what does that denote? So my small gamma ijl is the ijth element of my gamma yl matrix, which is nothing but given by covariance between yit and yit plus L, okay. So covariance between yit and yit plus L. So the same series but at two different lags, so t and t plus L, okay. So these are some sort of extension that one can gain insights on once you define some multivariate processes. So be it VARMA or VMA with certain order or VAR with certain order and so on and so forth. So can we sort of put forward some conditions of stationarity is the first thing. And can we sort of interchange the equation to take the other form? For example, VMA becomes VAR with certain order, of course. VAR becomes VMA with certain order, right? And then the last thing would be to put forward expressions for autocovariance matrices and obviously autocorrelation matrix. So lastly, the correlation matrix takes this form. So the individual correlation coefficients are given by this, right? So rho ijl is nothing but the covariance divided by square root of the variances. So gamma ijl divided by under root gamma ii0 into gamma jj0, of course for all the indices. So for all ij between 1, 2, 3, 4 up to k. Or in general, my autocorrelation matrix, which is given by rho yl, takes this form, right? So one thing to note here is that the expressions, the formulas stay the same, right? So the expression for finding out the autocorrelation matrix is nothing but v to the power minus half into gamma yl into v to the power minus half, okay? But then here, what does this v to the power minus half matrix becomes is it takes this form. So you have a matrix which is k cross k, of course, and then all the diagonal entries are 1 divided by under root of gamma 110, then gamma 220 up to gamma kk0, right? And all the off diagonal entries are zeros, okay? So if you plug in this v to the power minus half matrix in the above expression along with my gamma yl, which is nothing but the autocovariance matrix, and sort of evaluate, then you will get hold of the autocorrelation matrix given by rho yl. Okay. So hopefully the ideas laid down particularly in this week are, or rather should be clear, if not all the intricate notations and equations. So idea is what? You are slowly transitioning from a single series to multiple series. So the moment you transition from a single series even to two series, then the interdependencies between the two series come into picture, isn't it? So then we have to talk about autocovariance matrices, autocorrelation matrices, cross covariances, cross correlations, etc. Okay. All right. So just to wrap up this week, or rather the theoretical part of that, so we'll sort of discuss or put forward some application areas just to sort of complement whatever theory we've discussed so far. Okay. So the first application could be seen in macroeconomics. So the first idea could be, let's say, something like this. So monetary policy analysis. So a V-ARMA model can help in analyzing the effects of, let's say, interest rate changes or inflation and other monetary policies on variables like GDP, unemployment and exchange rates. Okay. So here again the whole idea is that can you sort of combine more than one time series processes or more than one sort of structures or features. So for example, here we are talking about a combination of interest rate changes, inflation and let's say other monetary policies and their effect on variables like GDP, unemployment, exchange rates and so on. Okay. So here one can actually adopt a V-ARMA process. So a simple ARMA process won't do the job because you don't have a single series, but then you want to study the interrelationships between 2 or 3 series or 2 or 3 features on 2 or 3 extra features. Okay. Or something like a second example would be coming from economic forecasting. So let's say governments and financial institutions use a V-ARMA process to forecast key macroeconomic indicators such as GDP growth or inflation, unemployment, considering the interplay between these variables. So for example, how is GDP growth related to or sort of affect inflation, or how does inflation is related to employment or unemployment, etc. Okay. All right. And then moving forward, the second application area could be in supply chain and operations. So the first example could be inventory management, right? So in industries with complex supply chains, a V-ARMA model helps forecast demand for multiple products, especially those with interdependencies, improving inventory management and reducing stockouts or excess inventory. So stockouts means what? Stockouts means that the inventory or the warehouse does not have enough products, right? So the stock is sort of out. So in other words, stockouts or excess inventory. So again, stockouts and excess inventory are on both extremes, right? So we want to avoid both. We don't want excess inventory, neither we don't want excess inventory nor we want stockouts, right? So one can actually apply V-ARMA model in inventory management, or let's say logistics and shipping. So shipping companies use a V-ARMA to forecast shipping demand and lead times for different routes and services, taking into account interrelated demand patterns across regions or product types. So one example here from a logistics and shipping point of view could be, let's say, if you want to analyze the interdependencies or the interrelationships between the demand patterns across regions. So let's say India and China, or India and let's say Sri Lanka, something like that. So let's say if you have more than one regions or more than one locations, and then for each region you have the individual logistics data or shipping data or inventory data, whatever. And then there, since you have two time series processes, this is an example of a bivariate sort of a situation. Okay. Another area could be in financial markets. So let's say asset pricing. So V-ARMA model are applied to study the co-movements between various asset classes such as stocks or bonds and commodities, helping in portfolio optimization and risk management, right? So again here a person could study the interdependencies between, let's say, how a stock is performing vis-a-vis, let's say, a government bond or commodity, let's say crude oil or something like that. Okay. And then the next example could be in volatility forecasting. So multivariate time series models like V-ARMA are used in predicting the volatility of multiple assets simultaneously and their covariance or co-volatility structure, which is critical in risk management and derivative pricing. Okay. So again, these are some examples coming from a financial sort of a framework. The next thing could be in energy market. So let's say electricity load forecasting. So a V-ARMA model could be used to forecast electricity demand, where multiple time series such as temperature, humidity and energy prices are interdependent and affect the energy consumption patterns, right? Or let's say oil and gas pricing. So in energy markets, a V-ARMA model help in forecasting the interrelated prices of, let's say, crude oil or natural gas and other energy sources. Okay. And probably the last one could come from, let's say, healthcare. So epidemiology. So V-ARMA model are employed in studying the spread of infectious diseases, where the number of cases in different regions may be interdependent, helping in resource allocation and public health planning. And another example could be, let's say, hospital resource planning. So hospital use a multivariate time series models to predict patient arrivals, demand for critical care beds and other resources, considering the correlation between different types of admissions. Okay. And now the very last one could come from something like climate science background. So temperature and weather forecasting. So in climate studies, a V-ARMA model helps in forecasting weather patterns by considering the interaction or interdependencies between various climate variables like temperature, humidity and wind speed across, let's say, multiple locations. And second one could be, let's say, air quality monitoring. So V-ARMA models are used to predict the levels of pollutants like CO2 or nitrogen dioxide and particulate matter, which are often interdependent in atmospheric conditions. Okay. So again, just to summarize very quickly in maybe a minute or so, is that whenever you want to model and forecast multiple series, so be it climate science, finance, energy, supply chain, logistics, wherever, right? So regardless of whichever area I want to implement in, but the whole idea is if you want to model and forecast more than one time series or more than one processes, then one has to apply some multivariate time series process structures or bivariate time series process structures. Okay. Now in the next session will be a practical session. So I think it's a strong suggestion that you should again rework or sort of review all the sessions so far in this week, so as to understand the application idea of, let's say, applying a V-ARMA process or a VAR process or a VMA process to some practical data much more confidently. Okay. Thank you.